Okay. Second question is an true or false question. We should determine whether statement is true or false. If it's true, we need to prove it, and if it's false, we need to give a given counterexample. And the first question was, determinants of a real symmetric matrix is always non-negative. Now, this is a false. Let's take the matrix. Let's take the matrix 1, 2, 2, 1. This matrix is a real and a symmetric matrix. Now let's look at the determinants. Determinants of 1, 2, 2, 1 is equal to 1 minus 4, which is minus 3, and this is a negative, so this gives us a contradiction. So this is a false statement. Part B, if A is a 2 by 3 matrix, then determinant A times A transpose is equal to 0. Now, this is again false. Let's take the matrix A is equal to 2 by 3, 1, 0, 1, 0, 1, 1. And A transpose will be equal to 1, 0, 0, 1, 1, 1. And this is the A transpose. If you look at the A times A transpose, which is equal to we need to multiply this row and this column, so we have 1 times 1, 2, and this one gives us 1. Then we need to multiply this row by the columns, so we will have 1 and 1 plus 1, 2. So determinant of this matrix, determinant of A times A transpose will be equal to 2 times is 4, 4 minus 1 is 3. So this is not equal to 0. So this statement is false. At part C, we have again a matrix A. If A is 3 by 2 matrix, then determinant A times A transpose is equal to 0. Now, for A, we will check again let's say this is A prime is equal to A transpose in the part B, and let's say A prime transpose is equal to A in the part B. So let's write here determinant A prime times A prime transpose is equal to determinant A prime times determinant A prime determinant of A prime transpose is equal to determinant of A transpose. Okay, this is determinant A prime transpose. Then this one is equal to determinant A transpose times determinant A, and this one is equal to determinant A times determinant A transpose. So this one is equal to determinant A times A transpose and we know that this determinant is equal to 3 from above, so this is not equal to 0, so this gives us a contradiction. So this part is also false. And part D is the question. Part D was, if A is a real square matrix then determinant A times A transpose greater than or equal to 0, and this is true, and we can prove it. This is true. Now we have determinant A times A transpose, right? And we know that this one is equal to determinant A times determinant A transpose. And we also know that determinant of A transpose is equal to determinant of A. So this is equal to determinant of A times determinant of A. So this is equal to determinant of A square, not A square. And we know that A is real, so determinant of A belongs to real numbers. So square of a real number is always greater than or equal to 0. But this completes the proof. Let's start to solve the third question. Suppose that a square matrix A can be written in the form A is equal to B, D, 0, C, where B and C are square matrix, and 0 denotes to the 0 matrix. Prove that determinant A is equal to determinant B times C. Let's try to solve this question. Let's say B is K by K matrix and C is S by S matrix. So entries of A's are equal to entries of B, Bij's, when I is less than or equal to K and J is less than or equal to K, and equal to Ci minus K, Ji minus K when I greater than K and J greater than K, and Di minus K to J when I greater than K and G is greater than K, and 0 if I is less than or equal to K and J is greater than K. Now for this question I want to use the Leibniz formula for determinants. Determinants, which is sigma of a symmetric group of K plus S product sine of sigma times product I from 1 up to n ai sigma n. Now I want to find where this product is non-zero. Now if I is on the set 1 to K, gamma i's must send again onto this set. Why? Because if I is less than or equal to K and J again, K plus 1, K plus S must be K plus 1 to K plus S. Now so our sigmas are sending to each set to itself, so these sets are disjoint on the sigma. We can decompose sigma S pi and gamma. Pi will be on the set 1 to K and gamma are the permutations on the set K plus 1 to K plus S. Now, if you look at the determinant of A, Also sine of gamma is equal to sine of pi times sine of sigma is equal to sine of pi times sine of gamma. Now, determinant A was equal to this one from the Leibniz formula for determinants. Now we can separate this one as sum pi from sk of sum gamma from ss signum pi times signum gamma times product I from 1 up to k ai pi I times I from k plus 1 to k plus s ai gamma I. Now this set is equal to gamma to sk, again same text, pi I, and we can now if we are in ai gamma I, we can see this one as, again, if you look at here, if I is greater than k and j is greater than k, we will see ci minus k, ji minus k, right? So this entry will be I from k plus 1 to k plus s ci minus k gamma I minus k. This one becomes I from 1 up to s ci gamma I. So we will have pi from sk, and also we can separate these sums because they are not related, they are independent of each other. So we have sum sine sine pi times I from 1 up to k ai pi I times gamma from ss sine gamma times I from 1 up to s ci gamma I. So this is equal to determinant of b, and this is equal to, sorry, these ones are bi, and this is equal to determinant of c. So this completes the proof. This is equal to determinant b times determinant c. Okay. Fourth question is, we need to find a matrix A, which is 2 by 2 matrix, is in the form is B, C, D, A, and B, C, D, A are all 2 by 2 non-zero vectors. Now, are all n by n matrix, and we need to find an example that determinant A is not equal to determinant B times determinant of A minus determinant C times determinant D. Now let's take B is equal to 1, 0, 0, 1, C is equal to 1, 0, 0, 1, again the identity, D is equal to 1, 0, 0, 1, and E is equal to, C is equal to 3, 0, 0, 1, and E is equal to 1, 0, 0, 1. Now, determinants of, if you look at these matrices, determinant of B is equal to 1, again determinant of D, and determinant of E, and determinant of C is equal to 2. So this is determinant B times determinant E minus determinant C times determinant. D will be equal to 1 times 1 minus 2 times 1 minus 1. Let's look at the A. A is equal to 1 0 0 1 1 0 0 1 2 0 0 1 1 0 0 1. If you look at the matrix, second row and the third row are equal. So determinant of A is equal to 0, which is not equal to minus 1. Now, fifth question is, let sigma be the permutation on symmetric group in symmetric group N, and such that sigma I is equal to n plus 1 minus I for each I 1 from N. Let's try to understand this permutation first. Now, if we take sigma 1 goes to N. Let's look at the sigma 2. N plus 1 minus 2, n minus 1. This goes like this, and sigma n goes to, for example, 1, and sigma n minus 1 goes to 2. So, if 1 goes to n goes to 1, 2 goes to n minus 1, n minus 1 goes to 2, again like this, 3 goes to n minus 2, and sigma n minus 2 goes to 2. So, every two, we separate in the two parts. So, we can say n is odd or n is even. If n is odd, we can separate this one as two cases. Case 1, if n is even, let's say n is equal to 2k. Now, we have, if n is equal to k, we have 1 goes to 2k, transposition 1 to k, and 2 goes to 2k minus 1, and k goes to sigma is equal to k goes to k. No, k goes to n is 2k, 2k plus 1 minus k, k plus 1. So this is the transposition, and we have k many transpositions. So if n is even, sine of sigma is equal to minus 1 to the k. Now, if case 2, if n is odd, then we can write sigma as 1 goes to, let's say n is equal to 2k plus 1, 1 goes to 2k plus 1, 2 goes to 2k, it goes like this, k minus 1 goes to, n is equal to 2k plus 1, 2k plus 1 minus k minus 1 is k plus 1, and k goes to 2k plus 1 minus it, and 2k plus 1 minus k is equal to k plus 2. Sorry, k minus 1, k plus 1 goes to k plus 3, and k, sorry, there is nothing, k goes to k plus 2, and k plus 1 goes to 2k plus 1 minus k plus 1 goes to k plus 1. So k plus 1 goes to itself. So we have again k many transpositions. So sine of sigma again minus 1 to the k. So it's so important to k. So we can write this sign of more properly. Now we can say that if n is equal to 4k, we can look at these cases in 4 cases. If n is equal to 4k, then we will have minus 1, let's say n is equal to 4s without confusion. If n is equal to 4s, we have our k will become 2s, so it will be even, so minus 1 to the 2s will be 1. If n is equal to 4s plus 1, then k become 2k plus 1, k become 2s. Again, we have sign will be 1. If n is equal to 4s plus 2, k become 2s plus 1. So sign will be minus 1. If n is equal to 4s plus 3, then k becomes 2s plus 1. So sign becomes minus 1. So this is the sign of sigma. If n is equal to 0 or 1 mod 4, then it's equal to 1. And it's equal to minus 1 if n is equal to 2 or 3 at mod 4. Okay, question 6 will be the let A be 6 by 6 tridiagonal matrix, namely Aij is equal to 0 if I minus j greater than 1. List all permutation in symmetric group 6, which is possibly give an unzero term in the determinant of A, and find their sign. Express the determinants in terms of the entries Aij with I minus j less than or equal to j. First, I want to understand the matrix A. Now, we have A, matrix A. Now, A1, 1 minus 1 is equal to 0 greater than 0, so it won't be 0. And A2, 2 minus 1, A1, 2, 1 minus 2 minus 1, absolute value of minus 1, 1, will not 0. But A1, 3 becomes 0, and these ones are become 0, since I minus j will gives us something greater than 1. Then A21 will be again 0 or non-zero. A22, and we have the entry A23, but after A24 we have the 0 entries. For the third row we have 0, A32, A33, A34, A34, 0, 0. Then we have again 0, 0 at the fourth row. First thing we have A43, A44, A45, 0, 0, 0, A54, A55, A65, we have again 0, 0, 0, 0, A65 and A66. Now, if you remember again Leibniz formula for the matrices, which was Leibniz formula was determinants A is equal to sigma in S of 6 sine sigma times product I from 1 up to 6 AI sigma I. This was the Leibniz formula. Now, we need to list the permutations which possibly give the non-zero term in the determinant. Now, to find the non-zero term in the determinant, this product must be non-zero, right? So, to have this product is non-zero, ai sigma I will be not equal to 0 for all I in 1 to n. So this this sigma must goes on these terms, not the zero terms. So let's try to find these permutations. So I want to find this permutation. I want to make a table. If you don't want to listen this part, you can go to the end. Now we have, let's make a table where 1 will go, where 3 will go, 4 will go, 5 will go, and 6 will go. This will be there. This will be our table. Now, if you look at here, 1 can goes to 1 or 1 can go to 2. So we have 1 can goes to 1. Let's look at these cases. If 1 goes to 1, 2 can, let's look at where 2 can go. 2 can goes to 2 or 2 can goes to 1. Let's again say 2 goes to 2. If 1 and 2 goes to 2, 3 can go to 2, 3 or 4. But 2 goes to 2. So 3 can not go through. So 3 can go 3 or 4. Let's say 3 goes to 2. Now 4 can go 3, 4 or 5. But 3 goes to 3, so 4 can go 4 or 5, so let's say 4 goes to 4. Again, let's say 5 can go 5 or 6, so let's say 5 goes to 5. And 6 can go 5 and 6, but since 5 goes to 5, 6 can go to the 6. Now, let's go through the cases where 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. And now 5 can go to 6 and 6 can go. If 5 goes to 6 must go to 5. Now let's continue the cases. 1 goes to 3, 3 goes to 3. And now 4 can go to, in this case 4 can go to 4 and 5. We look at the cases where 4 goes to 4. Let's look at 4 goes to 5. If 4 goes to 5, 5 must go to the 4. Why? Because something must go to the 4, but everything goes to the other thing, and 6 cannot go to the 4, so 5 must go to the 4. So then 6 must be go to the 6. Now we will continue. 1 goes to 1, 2 goes to 2. I think 3 goes to 3 cases are okay. Now 3 can go in this case, 3 can go to the 4 other than the 3. If 3 goes to the 4, 4 must be go to the 3, because something must go to the 3, but there is no other cases. So 4 must go to the 3. Then 5 and 6 itself. And there's another case. In 1, 2, 4, 3, 6, 5. We have also this case. Okay. I think we finished this case. Now we can change the 2. 1 goes to 1. 2 can only go to 3 now, since 1 goes to 1. 3 must go to the 2, since 2 goes to the 3. And 4, 5, 6 can go to itself. And for this one again, 1, 2, 3. 4 can go to the 4, 6, 5. 1, 3, 2, 5, 4, 6. I think these are all cases. Okay. Now, okay. Now, 1 goes to 1 cases are over. Now we need to look at what happens if 1 goes to 2. If 1 goes to 2, 2 must go to the 1 because something must go to the 1. But if the j is greater than 2, that entry cannot go to the 1. So we have 2 goes to 2. Again, these all can go to the itself. Then 2, 1, 3, 4, 6, 5. We have again this 1, 2, 1, 3, 5, 5, 4, 6, 2, 1. Okay, 3. Let's say 3 goes to 4. This must be 3, 5, 6, 2, 1, 4, 3, 6, 5. I think these are all the cases we have. These are all the permutations we have. If I write these ones in the correct one, this is the identity and sign sign of identity is equal to 1. Now this is equal to 1, 2, 3, 4, 5. They are going to the itself, so we can express this permutation as 5, 6. So we have only one transposition. So sign of 5, 6 is equal to -1. This is an odd permutation. Now, this one is 1, 2, wait, I did a mistake here. Okay, no, sorry. 1 goes itself, 2 goes itself, 3 goes itself. We have 5, 4. This is again sign of this one is again -1. This one is 3, 4. And sign again -1. This is we have 1, 2, 3, 4, 5, 6. So sign will be 1. If you look at this one will be 2, 3, and the other ones are the same sign, will be 1. Sorry, sign will be the -1. And for this one, 3, 2, or 2, 3, sorry, 2, 3, and 5, 6, sign will be 1. And this one this permutation is 2, 3, and 4, 5. So sign is 1. This one is 1, 2, only the 1, 2. So this one goes to -1. So this is 1, 2, 5, 6. This one is 1. Sign of this one is 1. This one is 1, 2, 4, 5. Sign 1. This is 1, 2, 3, 4. Sign 1. And this one is 1, 2, 3, 4. 5, 6, and the sign is minus 1. So we find all the permutations. Now, if we write more properly, first one was, okay, now I find all the possible permutations. Now I need to express the determinants in terms of aij's. Now, determinant of A is equal to, now, first non-zero permutation. Okay. First non-zero permutation was identity. So we have sign of identity, I from 1 to 6, A1, 1, I, then plus sign of this one, 5, 6 times, and here we have 1 goes to 1, A1, 1 plus A2, 2 plus A3, 3, A4, 4, A5, 6 plus A6, 5, and plus this one, sign was minus 1 at 5, 4, say minus 1, A1, 1, sorry, times, these ones are times, A1, 1 times A2, 2 times A3, 3 times A4, 4, sorry, A4, 5 times A5, 4 times A6, 6. And let's look at this one, 5, 4, okay. Let's look at the 3, 4 plus 1, sorry, 3, 4 again minus 1, A1, 1, A2, 2, A3, 3, A3, 4, A4, 3, A5, 5, A6, 6. And you can write the determinants continue in this way, and this is exercise, and I'm leaving this one as an exercise. Seventh question is, find the quotient and the remainder when fx is equal to x to the 4 minus x plus 1 is divided by gx, which is x minus 1 in F3. Finally, now we have x to the 4 minus x plus 1. We need to divide this one by x minus 1. Now we have x cubed. If we multiply by x cubed, x to the 4 minus x cubed. Subtract it by our main polynomial, so we have x cubed minus x plus 1. Then we have x cubed, so we need to add x squared, x cubed minus x squared. Then we will have x squared minus x plus 1 plus x squared minus x. So we have 1. So remainder is 1. And x cubed plus x squared plus x is the quotient. Eighth question is, find the greatest common divisor dx of three polynomials. f1x for x squared plus 2x, f2x is 2x cubed plus x squared minus 2x minus 1, f3x 2x to the 4 plus x cubed minus 2x squared plus x plus 1 in Q of x. Find the polynomials g1, g2, g3 such that g1 f1 plus g2 f2 plus g3 f3 is equal to 1. Now we need to, we can say that greatest, to use the Euclid algorithm, we can use the fact that greatest common divisor of f1, f2, f3 is equal to greatest common divisor of f1 of greatest common divisor of f2, f3. First we can find the greatest common divisor of f2, f3, and then we can find the greatest common divisor of f1 and greatest common divisor of f1, f2. Now, let's use the Euclidean algorithm to find the greatest common divisor of f3, f2. Now we have f3 is 2x to the 4 plus x3 minus 2x squared plus x plus 1 and divided by 2x cubed plus x squared minus 2x plus 1. Now we should multiply this 1 by x. Then we have 2x to the 4 plus x cubed minus 2x squared plus x. Okay, did I write the question wrong? Okay, there's no. So we have 1. So the greatest common divisor of these polynomials are greatest common divisor of f2, f3 is equal to 1. 1 then. So if this is 1, greatest common divisor of f1 and 1, it's again 1. So there is no problem. Sorry, I had a mistake. This one should be minus 1. If this one is minus 1, this one is big. Minus 2, so this will become 2x plus 1. So we didn't done yet. We need to divide this one by this one. So we have 2x cubed plus x squared minus 2x minus 1 divided by 2x plus 1. Now we have x squared, 2x cubed plus x squared. So we have minus 2x minus 1, minus 1, minus 2x minus 1, 0. So since this is 0, 2x plus 1, 2x plus 1 is the greatest common divisor. So greatest common divisor of f2, f3 is equal to 2x plus 1. Now I need to find the greatest common divisor of 2x plus 1 and 4x squared plus 1. So f1 x is 4x squared plus 2x, right? So if we take 2x common parenthesis, we have 2x plus 1, right? So f1x divisible by 2x plus 1. So greatest common divisor of f1x and 2x plus 1 is equal to 2x plus 1. So greatest common divisor of f1, f2, f3 is 2x plus 1. Now we need to write, so this is the dx. 2x plus 1 in terms of f1, f2, f3. Now from here, we can see that, for x squared plus 2x minus 2x times 2x plus 1 is equal to 0, right? But we want this one in terms of 2x plus 1, right? So we can write that for x squared plus 2x minus, I can add 2x plus 1 here, plus minus 2x plus 1, 2x plus 1 is equal to 2x plus 1. And from here, we know that 2x plus 1 was equal to f1x minus x times f2fx from here, from this multiplication, since this division, we have this one. So we can replace this 2x plus 1 by this one. Then we will have 2x plus 1 is equal to 4, which is f3x plus minus 2x plus 1 times this one, we should replace by this one, f1x minus x times f2x. So we have 2x plus 1 is equal to 1 times f3 of x plus minus 2x plus 1 f1 of x plus minus 2x squared plus x f2 of x. Sorry. Sorry, this one is f3, this one is f2, okay, this one was f1, f3, f2, f1, f3, f2. So g1 of x is equal to 1, constant polynomial. G2 of x is equal to minus 2x plus 1, and g3 of x, and g2 of x is equal to minus 2x plus x. Last question is question 10, which is let f be a field and g1 and g2 two ideals of fx. Part A, show that g1 intersection g2 is an ideal of fx if g1 generator of g1 is equal to f1 and generator of g2 is f2. What can you say about the generator of g1 intersection with g2? Exercise 4, show that g1 intersection g2 is an ideal. Now I will show that my claim is g1 intersection g2 is generated by least common multiple of f1, f2. Now one side g1 intersection g2 is in the least common multiple of f1, f2. Is under the ideal least common multiple of f1, f2. Now take hx from g1 intersection g2. Now we have just hx in the g1 intersection g2. Hx is in the g1 and hx is in the g2. So this implies that fx divides hx and g of x, f1 divide h of x and f2x divide the h of x. Now we need to show that least common multiple is in the here. Since both of them divide the h of x, then least common multiple of f1 of x, f2 of x divide the h of x. So h of x in the ideal generated by least common multiple of f1, f2. Now we need to show the other side also. Ideal generated by G1, G2 is under G1 intersection G2. Now, again, let's take G of X in this ring, this common multiple of G1, G2. So, least common multiple divides G of X. So, since least common multiple divides G of X and F1 divide least common multiple and F2 divide the least common multiple. So F1 and F1 divide G of X and F2 divides G of X. So F1 is in the G1 and G of X is in G1 and G of X is in G2. So this implies that G of X in the G1 intersection G2. This completes the proof.